Thank you. So today I'm talking about Lustre 217 and beyond. Peter did mention that I'd be covering some 216 material, and I do have some references to 216. I have been trying to focus more on future features. There's been quite a few. If you're interested, there's lots of presentations from me talking about earlier features. So Lustre has been around quite a few years, and it's important to note that we're still doing lots of interesting development. Despite the fact that, depending on who's marketing material from competitors, Peter mentioned, because Lustre is been around a long time, it doesn't work well with Flash or whatever. But the truth is that, Lustre actually can work very well with Flash. And what's even more interesting is that the newer Flash technologies like QLC Flash actually have properties that are benefit from the fact that Lustre has, the ability to do aligned writes and things like that. So, we have been doing lots of different work, still being used in, the largest fraction of HPC systems, but also very active in AI and machine learning. I think the, marketing number from DDN is over 500,000 GPUs running on Exascaler, and it's not a static world. To keep performance going on the newer computers, the DGXs of the world that are very common today, needs some ongoing effort. And we can scale up the client side. It's remarkable that a single client today, has a terabyte or more of RAM. They have, 192 or 256 cores, right? These are, what used to be a cluster of computers back in the day when we started. But we can scale up performance, tens of gigabytes a second per client. And so all of these things are ongoing, and we continue to do development for these kind of scaling and features going into the future. Quick architectural overview if you're not super familiar with Lustre, but I won't spend much time here. The interesting thing to take from this slide is that Lustre is managing storage in all parts of the cluster today, right? We have, the traditional OSTs, remote OSTs with different types of technology, Flash and HDD, QLC Flash, coming soon, compression and erasure coding. And then we can also do storage in the client compute nodes. The Lustre PCC feature is managing transparently the storage in the client. And so this is actually simplifying data management as well. Scaling up the number of clients. We actually have production systems, doing 40 or 50 MDTs in a single cluster, hundreds, to thousands of OSTs. And, my joke for people who ask, how big can Lustre scale? And I say that the limit on Lustre scalability is really with people's bank account more than how big are the numbers that we can scale. And it's not just a matter of, back in the day when, let's say, RiserFS was developed, 15 or 20 years ago, it's like, oh, this is a 64-bit file system, it can scale up to an exabyte. But that's not really true. That's just, the theoretical number. But Lustre actually, I think today could easily be an exabyte in size. Just nobody wants to, put all of that in one system. So the major features coming up, I've taken off 216 because it's pretty much done. Starting with 217, we actually have already a number of features that are pretty much developed, and they're coming up into a future release. I'm going to talk about these individually largely, except for the ones that have their own presentations already. So hybrid I/O is a very interesting I/O performance improvement. Dynamic node maps, that's virtualization and subtenancy, which has gotten quite a bit of interesting development recently. In 2.18, client-side compression has its own presentation. 2.18, again, we already have a number of features that are well under development for that. The 2.16 development cycle was quite a bit longer than we expected, so there's a bit of a backlog in terms of features. And so, these release numbers, I'm not 100% sure of, but I mean, definitely 2.17 is all of that work is largely finished. 2.18, some of this work is like the write-back caching. We actually have quite a bit of code there, and it's been under development for more than, I think, 2 years already. Erasure coding had some work started a few years ago, and James Simmons will be talking about that. Lustre metadata redundancy, I have a slide on that. It's basically just to harden and improve the availability of Lustre. And then in 2.19, these are a little bit more speculative in terms of when people will be working on them, but the projects are understood. Write-back caching 3, I'll get into the details of that, and metadata redundancy 2 is mirroring, so at the MDT level. So here the big news in the LNet world is IPv6, and that's, for some sites, that's becoming increasingly important. For many sites, it's okay because Lustre sits typically in a data center that is not directly connected to the outside world anyways. So having direct IPv6 connection into the file system is not super critical. So this has been held off for quite a while, but it's actually, some of our customers are, looking at having IPv6 across their whole internal network now. And making that, configuration-wise, making that all work is largely done in 2.16. There is some work in 2.17 that's still needed, like dynamically configuring server NIDs is I'm not saying about DHCP exactly, but being able to mount an OST on any of a number of servers and have the IP addresses automatically appear on the clients so that you don't have to, do lots of complex configuration changes when a server moves or gets readdressed. That kind of stuff is partly done, but still needs some work in 2.17. And another interesting one, having an MGS with multiple NIDs. You'd think, how many interfaces does a server really need? But what's happening these days is failover to 4 different servers for redundancy, and then having multiple interfaces per each server, and then having virtualized networks for multiple tenants within the cluster. So they'll have multiple LNet networks, and each one gets a different interface. We're hitting the 32 NID limit, and it also makes, aesthetically, from my point of view, makes the command line, mount super ugly because you have 200 characters of NIDs just as the mount device. And so handling that more transparently and being able to handle all of the different interfaces is something that will come, I think, soon. And another thing that came up in conjunction with the client-side data compression is sparse reads. That on a sparse read, we actually transfer, sparse write, we only transfer the data that's actually written to the server. But on a sparse read, the client, doesn't know whether all of the data pages are allocated or not. So it allocates a full-size array for the megabyte of data that it's reading. But if only half of that data exists on the server, we still actually do the data transfer to zero out all of the pages in the client. And in the client-side data compression, because the let's say you have a 2 times compression ratio, you get half of the space is only used, and so we're actually sending more data on the read than we need to, and so we're putting in a protocol optimization. It's not compression specific, but compression benefits from it, and so that's something that's already underway. So the hybrid I/O, there's a very interesting presentation by Patrick Farrell at the last LUG, and so if you want to know more details about hybrid I/O, you should see that one, but it's very worthwhile to mention here. And it's essentially trying to get the best of both worlds between buffered I/O and direct I/O. And so one of the issues with direct I/O, of course, is that applications have to be developed and understand how direct I/O works. They have to do their own buffer alignment. It has to be sized appropriately. And that makes it, harder for applications to do. And these days, I have something called the lazy programmer model, which is that users, it used to be that users were the inexpensive part of a supercomputer, and it was the hardware that was the expensive part. And so the users would spend a lot of time optimizing their codes and understanding where all their time is being spent. And now it's flipped around that the users are the expensive resource and the hardware is less expensive. So people spend a lot of time, they develop their code, and if they want it to run twice as fast, they just run, spin up twice as many VM instances, and they hope that it goes faster, right? And so we need to do a lot of work in the file system level to understand, what is it that the application is trying to do, and optimize it at the lower level, because lots of users don't even know, through 5 or 6 layers of abstraction and libraries, they don't know how their application works or what kind of I/O model it has. And so we really have to understand that at the lower level. And the hybrid I/O is trying to address that issue. And what had used to be thought of, it's interesting, I mean, Patrick gave also a presentation at FAST about this, that it used to be thought that the data copying from user space to the kernel is what made the difference between buffered I/O and direct I/O performance. But it turns out that it isn't the data copying part that's the expensive. It's inserting all of the pages into the page cache and then removing them from the page cache. If we're doing, gigabytes, tens of gigabytes a second on a client, that's millions of pages being inserted and removed from the client page cache, per second. And so that has quite a high overhead. And so only 10% of the direct I/O, benefit is in the removal of the data copy, and 90% of the benefit is because you don't have to lock the memory structures and insert and remove these pages. And so what we've seen here is that at small I/O sizes, buffered I/O is still faster because you're not doing synchronous I/O from the client to the server for very small transaction sizes. But once we hit about a megabyte, the benefits of direct I/O take over. And so by having an automatic switch inside the kernel to go from buffered to direct I/O, we can, essentially you can see the red line is tracking hybrid I/O. It can almost get to the peak performance of direct I/O as the I/O size gets larger. And this really helps the applications without the applications having to do any of the changes themselves. And it handles, unaligned memory because we have a double buffer. We allocate memory in the kernel and copy the data from user space if it's unaligned, and then immediately submit the properly aligned I/O to the servers, and then free that up as soon as we get a response back. And so that's given us quite a nice improvement for applications, and there's a lot more information about this on the in Patrick's presentation. And this slide is actually something you usually don't get to talk about, is just all of the little things that go into Lustre on an ongoing basis. And, usually I focus on what are the big features, what are the highlights, but there's always a steady stream of little improvements that go in, and I think that they don't, often get enough attention. And this one, is talking about a bunch of improvements done to the user tools, LFS find, LFS df, make dir, and so some of these were just done in the last few months. So for instance, LFS df, allow showing only the MDTs or OST space usage, inode usage, and things like that. I found that, on large systems, you have 500, OSTs, you do LFS df, and then you have to scroll back your screen, to find out, oh, what is the MDT usage, right? And this one, you can say, only show me the MDTs for LFS df. And actually another minor enhancement that I've filed a ticket for is to be able to show, the space usage for just a single OST, or, you can get this out of proc as well, but it's just nice to have it as part of df. A number of contributions from Los Alamos lab about LFS find to find specific files with xadders or attributes like immutable or read-only and things like that. LFS find -printf, so you can print out, the regular attributes that you can with regular find, path name and things like that, but also Lustre specific attributes, so you can generate your own output format that includes, like path name, timestamp, stripe count, pool name, various Lustre specific attributes getting printed out, and LFS find -ls. Another interesting one, LFS find -skip. So if you're doing an OST, you add in new OSTs, and generally I tell people, most of the time Lustre will just balance it out by itself over time. You don't have to actively do migration, but if you really want to migrate, to the new OSTs, you run find, and then you start migrating data from the old OSTs to the new ones, but then you get this sort of imbalance because you're just finding every single file and migrating a whole bunch. There's a new option -skip that allows you to say, give me only 10% of the files that it would match, right? And so then you can say, it picks it randomly, but you say 10% or 20% of the files, and then you only migrate those ones, so that it gives you, 10% of this directory and 10% of that directory, et cetera, as you go through the file system, rather than, 100% of the first directory and 0% of the second directory get migrated, right? So it's just a nice little enhancement. We can do overstriping on directories now. That's shown up as improving performance, granted for benchmarking, but it is, if you have a very large directory and lots of contention for high numbers of threads, but you only have 4 MDTs, you can say, oh, stripe this directory over 16 stripes, and they're each locked separately at the server side, and so that gives you some improvements. Another one, overstriping, is essentially for regular files. You can overstripe a regular file across multiple stripes on one OST, and again, that's good for highly contended, file workloads on a single file. But an enhancement, a usage enhancement, is you can specify LFS set stripe -c with a negative stripe count of -2 or -4, and that will say, put 2 stripes on each OST, or put 4 stripes on each OST, right? So that it's just a nice way to not have to calculate, oh, there's 27 OSTs and I have to write in, 54 or 108 into that number there. It'll work it out for you. List param, --path that's come up a bunch of times for scraping tools. You're doing Prometheus exporters or you're running your own monitoring tool, and you want to read instead of, it's recommended to use, L-control get param to get the parameters because they can move around based on the kernel version and things like that. But now you can set that up so you can do the direct reading from the path name, but you don't have to hard code the path into your application. You can use this --path. It will tell you on the current system, where that parameter file is located, so you can read it directly, but then you're not hard coding in proc fs lustre, blah, 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 that might change in a later release. More upcoming things, ELT list param with dash tunables. It will tell you, ignores all of the stats files and things that, are not actual parameters. So this gives you a more concise list of, what's been configured on a file system. And a later enhancement to this will be only reporting tunables that have actually been set since the file system was mounted. So you can see immediately in a short list of which parameters have been tuned on a client. And so that's good for debugging and things like that. The users swear up and down they didn't change any settings, but now we can see, oh yes, you did. You changed, this parameter, and that's why your performance is bad or whatever. Another actually really nice one is the merge, so that you can say, get param, whatever, max pages per RPC. And so it will aggregate, all of the ones from your 500 OSTs, down into one line that says, oh, they're all, 16 megabytes. Oh, but except for this one is 4 megabytes, right? It will point out if there's a difference between two and colorize them so that you can see, some of these things are set differently than the other ones. And, it's useful for debugging. It's nice just for reporting so that you can see the aggregation more concisely, but it's also good for debugging if you get inconsistencies between one MDT and another or whatever. Mount.lustre, having client-side mount options so that you can specify different parameters on a specific set of clients. You have fat memory nodes that want different max RPCs in flight or max 30 MB. You can have an etc, Lustre, client.fsname.param, and then it will, whenever that file system gets mounted on the client, it will apply a different set of tuning parameters specific for those clients, right, instead of the global tuning parameters. And having named projects is something that XFS Utils has, and the Lustre project tools are also using the same interface as XFS, but we don't support the named projects, and so this is just adding an ease of use option. So other higher level improvements, being able to mount thousands and thousands of devices. This has happened, if you're not so much because somebody has a 10,000 OST file system, but rather because of containers. They have, they want to mount a, 32 times of 1,000 OST system. And so each mount point has its own instantiation of all the connections. And so that's come up as an issue. Lots of people working on upstream client support. That's an ongoing task. Having exclude lists from cores, right? One of our, competitive file systems, they bind, and consume 100% of, 2 cores on every NUMA socket. And so that is, causing performance issues, so we can now easily exclude sockets. What else? Project quota aggregation. This is a relatively new request, but I think we'll be able to get it in the 217. It's similar to pool quotas, but it's come up that people want to account for multiple projects as having one limit. So you can use a fine-grained project ID per directory, but you have actually multiple project IDs being subject to one limit, right? So it's good for virtualization, and these 1,000 IDs are constrained to 1 terabyte of space, and it doesn't matter how they have limits individually, but it's just all 1,000 are subject to one upper limit. And what else? Oh, erasure coding. I mean, James is going to be have a separate presentation on that. This one also, Artem will be talking about client-side data compression, so I won't really cover it very much here, but it's pretty important and interesting feature that's helping use space on the server more efficiently, and I think it will really help us in some types of workloads. And the important thing here being that, of course, the majority of the compression is being done on the client, where there's tons and tons of CPU cores, instead of being done on the server, which is constrained resource. I won't get into all these graphs about compression ratios and things. What else? On the server side, we've done a bunch of improvements on rename. There was some of the workloads that have actually been moving off of HDFS and Apache. They expect to have kind of not sophisticated storage, right? So S3 and those backends, they don't allow partial file writes and things, so they have to work around these issues in the library. And so what happens is they're writing all of the data into a staging directory until it's complete, and then they rename the data out of the staging directory. And this is mainly a workaround for non-POSIX file systems. We don't need to do this for Lustre, but that's how the workload works. And so we had some sites where every single file in the file system is renamed after it's created. And so that was actually, hitting some bottlenecks. And so we improved, the directory rename and file rename performance and allowed more parallelism there. And we now allow, because of the DNE3 space balancing, which I don't think I talk about anymore. It's in my previous slides. But the MDT space balancing allows, creating subdirectories on different MDTs, but that kind of defeats the ability to have optimized renames. And so one of the additions is allowing an exclude list for subdirectory creation, so that the _ temporary directory that Apache Spark is using to stage is always created in the same MDT as the parent. So when you do the directory rename from temporary back into the parent, it's always on the same MDT, and the renames can go quickly. OST sizes, are hitting, for the disk side at least, OST sizes are in excess of a petabyte now, just because of declustered RAID and large drive sizes. Individual hard drives are in the, 12 to 20 terabytes now, and you put 40 or 80 of those into one OST, they're getting pretty huge. So we've done some improvements for large OST sizes. From my point of view, I mean, that used to be a whole file system, and now it's one OST. So, things have gotten pretty big now. Billions of objects on a single OST is pretty common now. On the performance side, one of the big improvements that's had some development is write-back caching on the OST. Currently, a Lustre OST either only does write-through caching, so it may still cache writes in memory, but if they're large, they don't get cached. And in all cases, the data was being, for LDiskFS at least, the data was being immediately submitted to the file system, and we only did asynchronous updates for the journal transactions. And so With the write-back cache on the OST, it allows us to aggregate very small writes to more efficiently use the storage on the OST. And this is helping, with things like hybrid I/O, so that you can efficiently do direct I/O of smaller writes to the servers, and then they get aggregated without waiting for disk sync on the server. What else here? In terms of usability, the OST pool spilling was a nice new little addition that's come out. Even though it's been, in the tree for a year, it's only in 2.16 being released now. This allows you to say, oh, if my flash pool is over 90% full, then start writing files directly to the disk pool so that you don't go 100% out of space. If you don't have any space management, there are tools that will do space management, in Exascaler, that's hot pools, and other tools, Lustre implementations may have other tools to manage the space. But if you don't have any space management, or your space management is not working quickly enough, you can force the disk, the OST allocation, to go directly to the different pool so that you don't run out of space. Better recovery handling, handling of read-only storage targets is nice. Online OST edition. It's always been possible to do online OST and MDT edition. There is a couple of race conditions if you're pounding on the file system while new OSTs are being added. You could get cases where some files know about an OST, or some clients know about one OST and other clients don't yet, because it takes a couple of seconds to propagate the configuration change. And so now the clients, if they, rather than reporting an error immediately saying, oh, I don't know about OST 407, right, they will stop and wait a second and retry until their configuration gets updated, and then they complete the read or the write to this file that was added on a different client. LL Job Stat, a very simple utility that you can run to try and find who is the offensive user that's pounding on my OST. Like, this guy is doing 4K IOs or creating a million files. I can run and tell you about which OSTs or which user jobs are causing the problem. And this is using the job stat facility, which has been around for quite a number of years. And that's actually one of the features of Lustre that is sort of unique, that we can track on a per process basis where all of the IOs are coming from on the server side, so that we can identify this. And another improvement that came from Los Alamos is the storing the user job name into an XAdder on every file in the file system. So it gives you a bit of provenance, so you can see, oh, this job ID is the one that originally created this file. And so if users are like, oh, I have all of this data, I don't know where it came from, you can check on the job ID. But it's also good for administrators. You can see, oh, is this the original job that created this file, or was it copied, or where did it come from? And that works in conjunction with, I was saying, the LFS find. You can, minus xadder user.job equals whatever. And so you can do a find and find the files that were created with that particular job ID, right? So it's just a nice little addition. Things coming in the upcoming release, adding a PFL layout on the file system at create time. People do this typically. PFL, I think, should be really running on every file system. It just makes life easier for users and administrators, not having to deal with, what is the right striping for this file and that file. And we've wanted to do this for quite a number of years, to enable PFL by default. And it's really been held up, not so much for a technical reason, but because the testing has prevented, setting this because it breaks, 100 test cases. And so we've had to go through, all of the test cases running with different types of PFL layouts to make sure that all of the test cases pass. And so that's work has finally been done. And so we'll be able to set this up out of the box. So whenever you run makefs.lustre, we'll just pick an arbitrary PFL layout, or have some option for you to override that in a specific way. But then everything will come up out of the box with PFL, and you won't have to set it by yourself a few seconds later. This is a small improvement, but. And then the other thing we were looking at is token bucket filter rules, just something out of the box. It's not necessarily going to be the ideal thing for every configuration, but to have some kind of rate limiting on, abusive jobs, because, you get your noisy neighbor problem that, one job is coming in and causing lots of load on the servers, and that's slowing down somebody else using the file system. And so, this is just something that lots of people ask for. How do I prevent this one user from consuming all of the resources? And so it's a little bit of a trade-off, because you want, everybody's job to run as fast as possible, but you don't want, one person, who, like I said, is sort of lazy programmer. They're like, oh, we're, creating one file for every variable in my, billion parameter model or whatever, and, abusing the file system for everybody else. On the LDiskFS front at the back end, we've been doing incremental improvements. One of them is for the trim, right? So managing flash storage more efficiently. It's possible to run FS trim and with makefs, but one of the issues that came up was you do a makefs and you've trimmed the whole file system, and then as soon as you mount it and the next time you run trim, it's going to trim the whole file system again. And that was not an issue when you had flash devices that were 20 gigabytes, right? But now we have flash that's getting into the tens of terabytes per OST, and so the amount of data that needs to be trimmed gets quite high, and so you don't want to have to redo that every time you mount and every time the system comes up. So we're making the trim flag persistent, and you can run trim fairly frequently then, and reclaim your space. The other one was formatting option, sparse super 2. It's just making the on-disk metadata more efficient for LDiskFS, and it's not really visible up at the application layer or the user layer, but it's for file systems over 256 terabytes, and for disks, hard disks, that's every file system. For flash, that's going to be coming up fairly soon. And MBAlloc, this is the low-level block allocator, and so that's gotten quite a number of improvements in the last few years, and so we're importing those for the distro kernels that don't have them yet. RHEL 8 and RHEL 9 don't have all of the MBAlloc improvements, which is, it's not that Google and IBM are working on Lustre per se, but they're working on ext4, and a lot of those changes are up only in the Linux 6.x kernels, and so we brought those back to RHEL 5 and, or sorry, not RHEL 5, RHEL 8 and RHEL 9. Hybrid storage. This is something we were playing around with. It's pretty interesting, allowing the start of the OST to have, this is mainly for the 1 petabyte size OSTs, that you can put the LDiskFS metadata on flash and then have the rest of the disk, spinning disk on disk HDDs, and trying to improve the performance of very large OSTs. And it's a little mini Lustre file system inside of LDiskFS. And so this is a bit of a prototype, but the code is largely there, and so we have to see, in which systems that's worthwhile to use. I already mentioned the delayed allocation. Same thing, this works with the write-back cache, right? Allowing you to aggregate more writes on the server. Parallel FSCK. I can't say that anybody's working on that right now, but it's a perennial wish list of mine, so I always feel if I list it here, then I'll be able to get somebody to work on it. But we did parallel FSCK for pass 1, and so that used to be the slowest part of the disk scanning. It was, taking 50% of the total time, and so now, with Amdahl's law, it's like we reduce the longest part down to 5% of the time. Now something else is the longest part, and that's pass 2 and 3. That's the directory scanning. So now we're going to attack that, I hope. This is actually, multi-tenancy is something that is come to be pretty important in the last couple of years. I find it a little bit ironic that, we spent, I'd say decades already, trying to aggregate up file systems, a number of servers and clients into be one huge file system. And now that we've done all of that work, they want us to split it up into smaller file systems. So, you can take your, 50 petabyte Lustre file system and split it into, 100 small virtual file systems. Anyways, so being able to handle this in multiple different virtualized environments. Sebastian will be talking about some of this, I think. But handling, capabilities on a per, restricting clients from, gaining extra authority in the file system, memory limits for clients, node map-based admin controls, which essentially allow you to specify fine-grained on a group of clients basis. Can they use change logs? Can they do quota configuration? Can they do administrative root operations or not? Even if they're root on the client, we can prevent them from doing it on the server. And what else? Actually, a new one that's coming in 2.17, the work is already done, is having a node map offset, so that if you have, say you have 100, tenants in a file system, you can easily assign them, a sub-range of the UID and GID and project ID space on the file system, so that, tenant 1 gets, range, 100,000 to 200,000, and the next one gets 200,000 to 300,000. And so as long as each tenant isn't using, more than 100,000 IDs, which is pretty safe, then you can split that up on the server very easily. Now we don't have to set up individual ID maps for those big ranges of IDs. What else? Oh, hierarchical node maps. I think Sebastian is talking about that. Backup and restore without an encryption key. We've been trying to get Google, we developed this ability to do raw backup and restore without a key, which in a big, site-wide file system, you can't expect users to be sitting there waiting to hear from the backup admin to enter their key, please, while I'm doing the file system backup, right? And more importantly, in the middle of the night when they're trying to restore from the backup, you can't expect users to be there, to type in their encryption key. But the problem being that in Google, this feature, fscrypt, is mainly used on Android devices, and they say, oh, well, we always have the key. It's stored in the key ring on the device when you log in, and when we back up to the Google Cloud, we just decrypt everything and then store it with a different decryption key in the cloud. And that is not practical here. So we can do the data migration and things, that's already been done, but the restore is actually the tricky part. And so, that's something that we want to get working as well. Metadata server improvements. So I think I was listing in here for a long time the MDT space balancing. I think that's one of the most important features that's come out in the last few years. And so that was already in 215. So I don't list it here, but we have still done a number of improvements in terms of recovery. I mentioned some of these: exclude list for the remote make deer, the user job. There's a number of improvements in performance and contention, in scaled directories, and I think the most important, interesting one, and I'll have a separate slide, is the metadata robustness, LMR, to try and make MDT0 less critical to the operation of the file system. Other performance improvements, I will talk about LMR in a minute, but performance improvements, this is just a nice slide that I stole from Shuichi that talks about things that we've done, or what we've done to improve the IO 500 benchmark over the years. And you can see we've actually improved performance quite significantly, even though the hardware, it changed a bit, but these performance improvements are, at a level over and above what the hardware has improved. And so both in terms of bandwidth and in metadata IOPS, we've seen some significant improvements over the years. In 216, this is one of the features Peter talked about, improved directory traversal performance. This is like batched stat ahead. And so this is really a foundational improvement for the the metadata write-back cache that I will talk about next. But we wanted to try and get some parts of the write-back cache done, into the 216 release, and then more of it will come in 217 and 218. So this is allowing RPCs that have multiple requests in them to optimize the network traversal, and we're just using it in 216 release just for LS-L, but it will be improved further in the future releases. Metadata write-back cache. So this is a huge improvement, almost 100 times in some of the workloads. It's mainly focused on single directory workloads, which is pretty common in machine learning and genomics and things like that, where you extract data into a directory and then you process it. And so this is focused on the single directory workload, and now a client can do, create, unlink, rename, setatter, all of those things. Tar and those kind of things are also, untarring a file would benefit from this, and copy minus R, whatever. So it's quite a significant change. The biggest benefit being no RPC round trip, so the client can do all of these operations directly in memory, and then it's still consistent, totally consistent across the cluster. So if, Schrodinger's directory, if you will, the changes aren't visible until you look at them from another client, but then they're still all protected by DLM locks. What else? Nice performance improvement. So this is Lustre, about 100 times. These are pretty impressive numbers this is, I think, a single client, or no, this must be multiple clients, I think. But no, it must be single client because it's largely restricted to a single client. MD test results. Erasure-coded files, I won't talk about this because James Simmons has a presentation on it. Metadata redundancy. So the first phase is mainly just taking services like MGS and the FID location database and things that are, central and only running on MDT0 right now, and making them more robust so that they can be distributed onto different MDTs or have replicated copies. And then later phases, which will be in 218, about having mirrored root directory and things. I mean, you can do mirroring, cross-device mirroring at a lower level, at the block level today, right, with DRBD and things like that, or iSCSI remote mirroring at the ZFS level, but this is going to be inside the file system and will improve the redundancy. And people always ask about Lustre is mainly POSIX. What is the is POSIX going to live? And I think POSIX will continue to live forever, because that's what is the common standard interface for applications, right? Lots of new applications they develop for one specific storage technology or whatever, but that's not portable, and most of those applications end up having to rewrite every few years because the I/O interfaces change, right? And so POSIX is the de facto standard. And Lustre supports lots of extensions to POSIX, right? IOU ring is the most common one, and that's a very interesting asynchronous data, but also increasingly metadata interface. And the issue is in lots of other file systems, they say, oh, we support a subset of POSIX. And it's like, yeah, but which subset? Like even today, we have crazy use cases where it's like, oh, we use the XADDR, we use an ACL to change an XADDR on a file that owned by some other user. And so if you don't handle all of those corner cases properly, then some applications are going to fail. And so it's my preference that applications that want to use some other behavior, they can either do so through tunings or new I/O interface, and they opt in to the new behavior rather than suddenly something breaking under an old application because it doesn't work. Read after write, has been around forever, and NFS still doesn't support that properly, and so some applications can't run on NFS, right? Anyway, so I think we're adding support for the new interfaces, and we can benefit from those, but you don't have to use them. I think that's the end of my presentation. Any questions?
Andreas, regarding billions of objects on OST, are we still happy with 32-bit inode number, or we need to extend it? On LDiskFS?
Most of the time, I think yes, right? We can, we're getting close to the LDiskFS limits, and there have been proposals. You worked on one, right? And I think that someday, in a few years, we might need that more than, 4 billion objects per OST. But today, I think it's still okay. And the improvements that were done there were mainly to aggregate object creation by time rather than just having, big directories that are updated randomly. They're grouped into smaller groups by time so that you don't have huge directories with, 100 million objects in them, but you get, 20 directories that are created with a couple million each, and then those ones will also stop being used and they can drop out of cache. And so we're much better at cache management and just handling large numbers of objects in general. But I think, we'll see whether we need, more than 4 billion. I think 1 billion is pretty, for most workloads, that's more than enough.
Okay, thanks.
A quick question on POSIX. Andreas, what arguments have you seen or heard for let's say, for using or moving to non-POSIX interfaces?
I mean, obviously, performance is one of the biggest drivers for that because, POSIX imposes certain restrictions that not all applications need, right? And so bypassing those restrictions are definitely possible, and I'm totally in favor of adding new interfaces like IOU ring. You can make asynchronous updates into directories, creating directory entries and things like that, or writing your file IO without having to wait for the completion. We're looking at adding tunables to allow, clients to say, oh yes, I'm sure I'm going to create all of these file names and they're going to all be different in this same directory. And so having those kind of extensions, I think, is definitely worthwhile. But the problem with going to non-POSIX is that you're tied into whatever other system. So, with if you have a DEOS interface or you have S3 or whatever, HDFS, now your file system, your entire application is tied to one specific file system. And I think every file system will have a POSIX interface, right? And you don't have to rewrite every time you want to change to a new technology.
So you're going to stick to the standard, extend the standard?
Yeah, well, and even if they're not official extensions to the standard, right, there's de facto extensions just because Linux is, overwhelmingly the only choice. So as long as Linux has that interface, and the library interfaces are the other thing, Adios or whatever, HDF5, if you're working those ones, we can optimize at a lower level, but I don't think it makes sense to program, your application for a specific file system.
I got a question about write-back cache. So you were talking about the V2. I'm trying to understand what's in V1 and...
the metadata write-back cache.
Yeah. And what's in V1? And do these admins have to do something specific to enable it, or is it working out of the box?
Metadata write-back cache 1 is essentially a fancy stat ahead, right? So it's totally transparent. So it's ls minus lr kind of workloads, and so it's prefetching attributes. But the reason this is considered under the write-back caching project is because it's adding batched operations. So you can fetch 100 attributes at a time from the MDS in one RPC. And so that's more efficient at the network level, but it's a precursor for the write-back caching too, because if you're doing, you created a million files in memory on a single client and you want to flush that all to the server, you don't want to do 1 million or 5 million because you did a create and then a set adder and a chown, a chmod, all of those things. You want to be able to just blast those things over to the MDS in huge batches and get efficient, cache flushing behavior. It's like if you write, 1 byte at a time to your data file, you don't want to have to send 1 byte at a time to the disk. You want to do it a megabyte at a time, right? And so the batching, RPC batching is the part of WCBC1.
And to support for actual write-back cache, so V2, does it require some specific setup locally in the client? Because in the past there was some discussion about using TMPFS in the background.
So this in memory it does use something similar to TempFS.
It's transparent?
MEMFS, yeah, it's transparent. And this will be activated essentially when you do a make dir, right? And so the applications don't have to do anything. I mean, there will be a tunable on the server that says, can clients use write-back caching? Of course, they'll have to negotiate at connect time, that clients even understand write-back caching. But it's, and the server will have to understand it. But it will mainly be transparent, and in, WCB2, it will be restricted to new directories, right? You'll create a new directory, you get an exclusive lock on it, you write, create all of your files, you can write them into memory cache, the data, and it will be flushing those either in the background or because of lock conflicts. So if another client tries to create in there, it will flush out the top level of the directory and then get write-back cache locks on all of the next level directories, etc., down the tree. So if one client comes in and only wants to ls-l some specific path name deep inside a write-back cache directory, we don't have to flush everything to the MDS before the client can get its response. We only have to flush the path that that other client is interested in. But in WCB3, we would, which hasn't been developed yet, don't get me wrong, but WCB3 will allow you to essentially get a write-back caching lock on an existing directory, and we would have to, redear all of the entries in that directory so that we know what names already exist, and then you'll be able to do in-memory operations that are not conflicting with existing directory names. So there's already a road forward to do it on existing directories, but the first phase will just be new directories.
Thank you.
Thank you. I think we are out of time to take other questions, so thank you, Andreas.